Okay, howdy from West Virginia, which I'm still not getting right. Oh well. But what I can get right is joke of the day, because it is the best part of the day and you cannot wait for joke of the day. Are you ready? Let's do this. So why are can crushers sad? You know, can crushers that you put your pop can, like a Coke can or a Pepsi can, you put it in there and you crush it. So why are can crushers sad? Because their job is so depressing. You know, pressing the soda can and so depressing. Anyways, what's not depressing is sets of numbers. So I'm going to take a look at sets of numbers with you and show you how the sets of numbers are built. Now, what some people like to do is they like to start with the largest set of numbers and they work their way down to the smallest set of numbers. Me, I prefer to start with the smallest set and work my way out to the biggest set of numbers. So let's take off with that. Now, mathematicians are not creative people. We call it like we see it. I say this all the time. Mathematicians are not creative people. We call it like we see it. And that's very helpful because that allows us to understand some of these mathematical processes. So what I'm going to do is I'm going to start with the smallest set of numbers, which are called the natural numbers. So let's start off here with our set of natural numbers. Natural numbers in there. Now, our natural numbers, if mathematicians are not creative, then how do you think natural numbers will occur? Absolutely, they'll occur naturally. So picture yourself in nature. Picture yourself out in the woods or maybe walking along the beach or what have you, but you're out in nature. Here in West Virginia, we are in the mountains. So picture yourself walking along this mountain path or this woodsy path. And as you're walking along this path, you've got these rocks that are along the path. And you need to mark those rocks. In other words, as you go along, you need to mark them off like this. What types of numbers would you use to mark off those rocks? Absolutely. You would go 1, 2, 3, 4, 5, and so on. So those are what we call the natural numbers because these are the numbers that occur in nature naturally. So what I have here is some popsicle sticks. They're going to represent the natural numbers. 1, 2, 3, 4, 5, 6, and so on and so forth. So this is going to be my set of natural numbers. Now what I'm going to do is I'm going to put this set of numbers all together in this little box and seal it up so that they cannot escape from each other. So what I have here, and you can see they're not escaping, what I have here is my set of natural numbers. And you can see it fits quite nicely, right, like that. Now, what if I take my natural numbers and I only add one number to that? If I'm only going to add one number, likely what number would I add to that? Absolutely, I would add the 0, something that looks like this. Now, if I take that 0 and I add it to this set of natural numbers, and 0 is the only thing that I'm adding, I'm creating a new set of numbers. So what I'm going to do is I'm going to take my natural numbers and my 0, I'm going to put them together in a whole new box. And I'm going to seal this box up so that they cannot escape from each other, all sealed up together. Now, because I've added the 0 to it, that 0 kind of looks like a great big hole. So what mathematicians do to make life easy, and because we call it like we see it, we're going to call this the set of whole numbers. So when I take these natural numbers right here, whoops, I've lost my marker. Take my set of natural numbers, let me put that back up, because I really want to use the same color here. But if I take my natural numbers and I add to that just a 0, and that's all, then I've created a new set of numbers here. And this new set of numbers, like I said, is what we call the whole numbers. Because that 0 looks like a great big hole. So all my natural numbers, throw in the 0 that creates the set of whole numbers. That's what we have right here. And you can see that, yeah, it kind of fits quite nicely there. So what I've done so far, if you take a look at it, is I've created something that looks kind of like this. And here's that 0. Here's all these natural numbers. 1, 2, 3, 4, and so on and so forth, and it's going to continue on forever in that direction. Now, what if I would take this little number line, loosely said, and I put a little pin right here where that 0 is. I take all this and flip it over that way, so that this unit of length, this 1 unit of length, flips back like this over to here, and it's still 1 unit of length, but it's 1 unit on the other side of the 0. Well, I need to designate that it's on the other side of the 0, not on this side. So what I'm going to do is I'm going to give it a symbol like this that says, oh, it's on the other side of that 0. So now what happens is this unit of 2 lengths, when I flip it over this way like this, and that 2 sits right back here, well, once again, that's 2 units of length, but on the other side. So to designate that, I'm not going to put another 2, because that's this one. I'm going to put a negative in front of it. And now that unit of 3, when I flip it over like this, it's going to sit back here. Again, there's that unit of 3, but I don't want it to be this, so I'm going to put a negative in front of it. And that's going to continue on with my -4, and so on and so forth, and it's going to continue forever in that direction. So now what has happened is I've got this set of natural numbers. I create their negative counterparts. So I've created a -1, a -2, a -3, a -4, a -5, and so on and so forth. And that's going to continue ever. So that's going to go with this set of whole numbers. Remember, whole numbers looks like a big hole, so that's all those natural numbers plus the 0. I'm going to put these together, and I'm going to put them in a new box, and I'm going to seal it up so that they don't escape from each other. There we go, locked up nice and tight. So this set of numbers, once we add in all those negative counterparts, so we've got our natural numbers and our whole numbers, and what we do is we add in all those negative counterparts, and what this does is this creates what we call the integers. So those natural numbers, like I said before, let's put some examples in here. Those natural numbers are like your 1, your 2, your 3, and so on and so forth. Throw that 0 in there. Now this creates the set of whole numbers. Throw in those negative counterparts, -1, -2, -3, and so on and so forth. But remember, the integers is not just this -1, -2, -3, and -4. It includes the whole numbers. It includes those natural numbers. So what we have now is something that looks like this. But as you look at this number line, there's some types of numbers that are missing in there. And you know they exist. You've seen them before. You've had to deal with them before. So you know that they exist. What types of numbers are missing? Absolutely. Decimals are missing. Like a 0.5 or maybe a 2.7 would be missing. Or maybe, for instance, a -3.6 is missing. What else is missing? Absolutely, fractions are missing. Like, for instance, maybe a 3 2/3 is missing, or maybe a 6/7 is missing, or maybe perhaps a -1 3/4 is missing. So yes, all the fractions and decimals are not in here, but you do know they exist. So when we take our integers and we throw those fractions and decimals in there, suddenly we've created what we call the rational numbers. The rational numbers. And so like I said, the rational numbers is going to be all of these numbers that you see here. All of those integers, which include the 0 and the natural numbers, but it now includes all those fractions and decimals. So we'll write in there, includes fractions and decimals. Box isn't quite big enough. There we go. Let's fix that. Now, there are some numbers though that, and you do need to understand that rational does not mean rational dude like in surfing. That's not at all what it means. In this case, rational means can be written as a fraction. Can be written as a fraction. These decimals can be written as fractions. However, there are some types of numbers that cannot be written as fractions. You've seen numbers, say for instance, like these are decimals that go on forever and ever and ever. They never repeat and they never end. So what we have, either it is rational and it can be written as a fraction, or it is not rational and it cannot be written as a fraction. Cannot be both. So I'm going to have another side over here. This is going to be my irrational numbers. Irrational numbers. And like I said, these cannot be written as fractions. Cannot be written as fractions. Because like I said, the definition of these rational numbers is that these can be written as fractions. Can be written as fractions. And that's the difference between your rational numbers and your irrational. Like I said, rational, not rational, dude. It means can be written as a fraction. So hopefully you've noticed that all of these boxes that I've chosen, I chose them very carefully. They all fit inside of each other. But notice that once we hit this idea of rational numbers, that as long as it can be written as a fraction, it's going to go into this box right here. So once I take all those integers and I throw all the fractions and the decimals inside this box, this is the set of rational numbers, because even these types of numbers can be written as fractions. However, it's either rational or it is not rational. Either you can write it as a fraction or you can't write it as a fraction. You can't have it both ways. So, like I said, I've selected my boxes carefully. Notice that these two boxes do not fit inside of each other. They won't. Now, granted, I can kind of do something like this, but notice how all of these nestled down inside of each other. So they were subsets or subgroups of each other. But these two, the rationals and the irrationals, they don't nest down inside of each other. Either it's rational and can be written as a fraction, or it's irrational and cannot be written as a fraction. So let's test this out. What we're going to do is I'm going to give you a little quiz here. I know it's kind of crazy. We've got this video and I'm doing quizzes, but you know, this is the best way to understand. And I'm going to hold up a number and you're going to decide, is it rational and can be written as a fraction, or is it irrational and cannot be written as a fraction? So let's try this out. Here is the number 2/5. So is that rational and goes in this box because it can be written as a fraction, or is it irrational and goes in this box because it cannot be written as a fraction? Absolutely, 2/5 is a fraction. So it's already under this definition that it can be written as a fraction. It goes in this box right here, the rational numbers. Let's take a look at another one. What about this? 3.5, 3.5. Can you write that as a fraction and put it in this box with all these rational numbers? Or can you not write it as a fraction and therefore it's going to be irrational and goes in this box? Which is it, rational or irrational? Absolutely, this is going to be a rational number. If you take 3.5, and many of you are saying, well, 3.5 is the same thing as 3.5, and you are absolutely right. That's the same thing as 3.5. But if you were to turn this into an improper fraction, remember, in order to turn it into an improper, you multiply these two. 3 times 2 is 6. Add this one, giving you 7. So 3.5 is the same thing as 7/2. There's that fraction, and remember the definition of rational here is can be written as a fraction, so it goes in this box, can be written as a fraction. Let's try another one. What about this? -17. Can it be written as a fraction and therefore goes in this box of rational numbers, or can it not be written as a fraction and therefore is irrational and cannot and has to go in this box? Which is it? Can be written as a fraction or cannot? Absolutely can be written as a fraction, because if you take any of your integers, any of these that appear to be whole numbers, including the negative counterparts, and all you have to do to turn those into a fraction is simply put them over a 1. Ta-da! You have a fraction. And remember, that is the definition of a rational number, can be written as a fraction. So it goes in this box right here. All right, let's test you out here. -2.18. What does this bar right here mean? Yes, that bar means that the 1/8 is going to go on forever and ever and ever, and it's going to continue to repeat. 1/8, 1/8, 1/8, 1/8, 1/8, 1/8. So this decimal, -2.18, 1/8, 1/8, 1/8, 1/8, 1/8, can it be written as a fraction or not written as a fraction? Now, there's a bit of a tedious process to do this, but surprisingly, this can be written as a fraction. In the scope of this video, I'm not going to go into the details of how to write this one as a fraction. That's another video. But yes, your repeating decimals can be written as fractions. So this is most definitely a rational number. It goes in this box right here, can be written as a fraction. Let's go ahead and add that over here to our rational numbers, not just decimals, but repeating decimals as well. Repeating decimals. So decimals that terminate, decimals that end, like the 3.5, but your repeating decimals as well, those can be written as fractions. All right, let's check ourselves out here. What about this? That's the symbol for pi. Remember, this deals with any curves and circles, pi. That is 3.14159265, like you see on Night at the Museum 2 with the Einstein bobbleheads, 3.14159265. And it goes on and on and on, and it never ends and it never repeats. So pi, is it going to be a rational number that can be written as a fraction and goes in this box, or is it an irrational number that cannot be written as a fraction, therefore goes in this box? Non-repeating decimal, non-repeating. Absolutely. Your non-repeaters are going to be your irrational numbers, and it goes in this box. So let's add that to our definition up here. Those irrational numbers, those are going to be the non-repeating decimals. Non-repeating decimals. All right, let's check just a couple more. How about this one? Square root of 2. Square root of 2. Can it be written as a fraction and therefore is rational? Or can it not be written as a fraction and therefore is irrational? Square root of 2. Well, square root of 2 is 1.414 but the idea here is it never ends and it never repeats. It is also a non-repeating decimal. So square root of 2, being that it is a non-repeating decimal, it is going to be irrational, cannot be written as a fraction, goes in this box. Last one. Negative square root of 3. This again is one of those non-repeating decimals. Negative 1.7 something. It goes on forever. It never ends, but it never repeats. That's the key. A non-repeating decimal is going to be that irrational number that cannot be written as a fraction. There's your definition of rational, can be written as a fraction. So it goes in this box right here. So hopefully this helps with your understanding of the sets of numbers. And again, it's much easier to understand them if you start with the smallest set, those natural numbers that occur naturally, 1, 2, 3, 4, 5, 6, and so on. When you add the great big whole to that, that creates the set of whole numbers, adding the 0 to this set. And then when you take all these and flip them over and add in those negative counterparts, now this whole set together is those set of integers like you saw whenever I boxed them all together like this. And either you can write it as a fraction and it's rational, which would be all of these within that set of rational numbers, or you can't write it as a fraction, which is basically your non-repeating decimals that continue on forever, therefore they're irrational. And notice these do not sit inside of each other at all. So I hope that helps. Have a great day.